So in this video, let's talk a little bit about efficiency and explain what this P versus NP thing I was talking about. So far, when we've talked about efficiency, we've been talking about the efficiency of a particular algorithm. And so two important distinctions that we're gonna make today in terms of our discussion of efficiency is we're gonna be talking about efficiency of problems rather than the algorithm that solves it. And so we'll say that a problem is solved efficiently if there exists an algorithm that can efficiently solve it. Notice that kind of leaves the door open where if a problem currently isn't efficient, meaning there isn't currently an efficient algorithm, it still could potentially be efficient. We just might not know that algorithm yet. And we'll also kind of use this weird definition of something to be efficient versus inefficient, which is it has a runtime that's polynomial and And what I mean by that is a polynomial runtime is some runtime that's big O of n to the k, where k is some constant number. And in our discussion today, we'll consider any polynomial time algorithm to be an efficient algorithm. Now, are they always actually efficient? Well, no. If you have something that's like n to the 1000, that's not really that efficient. Fortunately, those kind of huge polynomial exponents generally don't happen in most real programs or most real problems that we try to solve. Generally, you might see something like n squared, n cubed, maybe if it's really bad, like n to the 5th. So those generally scale much, much faster than something that might be, say, exponential time. And so in some sense, saying that polynomial is efficient is a very, very low bar. It's at least saying, well, at least you're not an exponential, right? That's kind of what we're getting at, is exponential growth is really, really bad for runtimes. So getting a polynomial time algorithm, even if it's a really bad degree, is still way, way better than one of those exponential things. To make that a little bit more concrete, this is a table from a very popular textbook that shows running times for various operations based on the running time. And you can see for most of our running times, n log n squared, n cubed, it's usually less than a second. Now, when it gets kind of larger, n is always really fast. N cubed starts getting really, really slow, all the way down to 31,000 years for an input size of about 1 million, which is, not that big of an input, but one thing to mention is that these numbers are a little bit outdated. They're probably from computers that are a little bit slower, but the trend is still the same. But notice that when we talk about these exponential runtimes, 1.5 to the n, 2 to the n, or even this very, very bad n factorial, even for moderate-sized inputs like 1,000, we're already at very long time. And very long in the definition of the textbook is something like 10 to the 25 years. That's a lot of years to only process 1,000 elements. That's wild. And so that's, in some sense, the motivation for why we think polynomial is similar to efficient. Now, this is also from the theory people perspective, where we're like, oh, wow, there's this problem that we thought had an exponential runtime for a long time, and then you found this like n to the 100 runtime. Well, that's great. It's no longer exponential, even though in practice, that might not actually run very efficiently. It's more of like a mental barrier kind of thing. So we're going to use the term polynomial and efficient interchangeably in this lecture. And that's kind of where the setup for all of these problem statements are going to be. So one quick aside before I introduce what is P, what is NP, is everything we're talking about today is with respect to these things called decision problems. And I have to just be a little bit pedantic because this comes from all the definitions, and so kind of important, which means all the problems of interest are ones where there's yes/no answers. So we call these decision problems, where the output of the algorithm has to be yes or no. Now, why do they have to be decision problems? This is mostly a historical quirk. The way that these things were defined back in the 70s, people are really interested in these decision problems, so all of the terminology came from that. And so all of the core definitions for the things I'm going to show you today really bake into it this idea of a decision problem. Now, this isn't that big of a deal. Pretty much any problem you can think of can be phrased as a decision problem. Instead of asking, how do I two-color this graph? You can ask, can we two-color this graph? Or instead of find the shortest path from S to T in a graph. Ask, is there a shortest path from S to T of length at most K? Now, both of these are kind of similar problems, but the second ones are always decision problems. The answer is yes or no. Again, I just wanted to mention this. It's not going to make a huge impact in our discussion, but you see this kind of qualification that has to be decision problems out there quite frequently, so I wanted to mention what that was. I'm going to be a little bit hand-wavy. I'm not going to rely anything about them being decision problems only, but I just wanted to mention that. So when we're talking about P versus NP, we're talking about two sets of problems. The first set is called P, stands for polynomial. And this is the set of all decision problems that have an algorithm that solves it in some polynomial time. So this is a set of problems. So problems like two coloring and short path. They're things that we know an efficient algorithm for. So this P is a set of all of the problems that we know that have an efficient algorithm that solve them. If you take almost any algorithm that we've talked about or any problem that we've talked about this quarter, almost all of them are problems that are in P, or to be pedantic, if you changed it to be a decision problem, would then be in P. If we saw a polynomial time algorithm to solve it, so something like n squared, n cubed, even that e log e business that we saw in a lot of our graph algorithms, all of that stuff is polynomial. It's bounded by a polynomial. P is what we call a complexity class. It is a class of problems that all kind of share this kind of complexity, meaning that they all are bounded by a polynomial runtime. So we generally refer to the set of P as the problems that we can solve efficiently. And so again, this is a very weird mindset to switch yourself to. P is a set of problems, not one particular problem. It's all possible problems that we know efficient algorithms do. And so this question of P versus NP, I'll explain what NP is in a second, is really a question of what can we solve efficiently? The question is, how big is this set P? Does it contain every problem of interest, meaning any problem of interest would have an efficient algorithm for? We don't know. So the big question is, how big is a set P? So to understand kind of what we're comparing against, we need to understand this other complexity class called NP. Before I define what that means, let me give you an intuitive description of what this other set is supposed to describe. So instead of trying to solve problems efficiently, this other set is concerned about knowing the answer when you see it. So it's the set of problems that if I gave you an answer to that problem, you can efficiently tell me whether that answer is correct. So you'll know the answer when you see it, right? You might not know how to find it from scratch, but if someone gave you an answer, you could verify it. So the set of problems are ones where if the answer was yes to the decision problem, and you had a proposal for how to achieve that answer yes, you could verify whether that proposal would actually make the output of your decision problem yes. So that's a very weird, abstract way of talking about it. Let me give you some examples. The problem of two coloring is, or whether a graph can be two colored, is a I'll know it when I see it problem. Because even if it's not obvious from the start, given a graph, how to solve it, if I gave you a two coloring of a graph, you could verify for me that it is a two coloring. You just look at the colors and make sure there's no conflicting edges. So even if you don't know how to solve an uncolored graph, if you're given a proposal answer, a two colored graph, you could tell me whether or not that's a valid two coloring. Similarly, if we're thinking about that short path problem, if someone told you, hey, I found a path in this graph with length at most k, you can verify that by just checking the path itself. So this I know it when I see it problems, or what problems that we call NP problems. Now, NP has a very weird definition, a very weird name. NP stands for non-deterministic polynomial. A very common misconception is that NP stands for not polynomial, because P stands for polynomial. But the N does not stand for not. It stands for non-deterministic. The set of problems in NP are exactly these I'll know it when I see it problems. Ones that you may or may not know how to solve efficiently, but if you were given an answer, you could verify that answer efficiently. So it's the set of all decision problems such that the answer is yes for that problem, and you're given some proof that's saying like this is how you to color this graph, then you can verify whether that's a correct proof or not. So the NP is all about verifying the correctness of a problem or the answer of a problem. So NP is just another complexity class. It's another set of problems. P is one set of problems, NP is another set of problems. The intuition here is that P is the set of decision problems that you can solve in polynomial time, and NP is the set of decision problems that you can verify a solution for in polynomial time. They're just two different sets of problems. The question of P versus NP is how do these two sets relate? How is P related to the NP? How is solving a problem related to verifying an answer to a problem? So one thing I want to mention is kind of a brief aside just to kind of remind you that this thing does not stand for not polynomial. That is not what NP stands for. That is a very, very common misconception. Please don't ever say that. A computer scientist cries every time they hear someone say not polynomial. It comes, the term NP, non-deterministic polynomial, comes from the computer science theory land. I don't know how no one thought that people wouldn't confuse NP for not polynomial. It was a bad idea in hindsight. But it came from this fact that sometimes theoreticians think about this kind of ideal computer that we call a non-deterministic computer. It kind of knows what to do at each step of the program. It kind of is able to divine, talk to God, and know what the right step is. This is not something that we'll actually have in practice, but is actually a useful theoretical tool for proving things. And so the history of kind of where these terms came from relied on this non-deterministic computer, hence we got non-deterministic polynomial time. But what I want you to understand is that NP means verify efficiently, while P means solve efficiently. Now, the fundamental question of P versus NP is how these two sets relate. It's actually pretty easy to show that P is a subset of NP, meaning any problem that's in P is definitely also going to be in NP, non-deterministic polynomial. If I can't formally prove that to you, but I can kind of argue it. If you're able to efficiently solve a problem, meaning it's in P, then you should already kind of get a verifier efficiently as well, right? You could just use your algorithm to solve the problem as your verification step. So someone asks you to verify this answer, just run the algorithm, you know how to solve it because that's efficient. And then you can verify the answer that they gave you. So any problem that's in P is definitely going to be in NP as well. But the question is, are these sets equal? So the big question is P equal to NP? And there's really two answers here, or two possibilities. Either they aren't equal, or they are. If they aren't equal, this subset relationship still holds. P is definitely a subset of NP. Anything that's solvable is also verifiable. So P, if they're not equal, P is a kind of subset of NP. There's this broad set of problems that you can verify efficiently, and then a small subset of them that we also have efficient algorithms to solve. Now, another possibility is that these sets are actually equal, and that P is equal to NP, which means if you're able to verify a solution, then you should be able to also solve a problem efficiently. And this sounds like a very abstract question. It has real important impact because this is fundamentally asking a limitation of computing. We're asking, is solving a problem just as easy or just as hard as verifying a solution? Is creativity something special, or is it just kind of something that you could derive from an algorithm? So to give you a bit of a spoiler, almost all computer scientists think that they're not equal. We think that P is not equal to NP. We think that verifying a solution to a problem definitely seems fundamentally easier than solving the problem itself from scratch. That there is something special about trying to solve a problem that can make it hard. Now, the thing that's a bit frustrating is people have been working on this for quite a long time, and no one has proven that. No one has proven that solving problems should be hard. There is no proof out there that says P is not equal to NP, or no correct proof at least. We'll talk a little bit about a lot of people try this, but no one has succeeded quite yet. So while most people think that they're not equal, it's really frustrating that no one's been able to prove that. No one's been able to find the reason why there's this inherent asymmetry between solving and verifying problems. So what I want to quickly talk about is some reasons you might care about this P versus NP problem, even though it is awfully abstract. So why should we care about this? So even though we're kind of convinced that P is not equal to NP, why do people talk about this so much? Well, it's your chance to win $1 million. This is one of the big open problems in math and computer science. There are lots of organizations out there that offer prize money for if you solve it. So if you were to solve this P versus NP problem, the Clay Mathematics Institute would give you $1 million. They also have 5 other problems that are open that also have $1 million prizes, but they're less applicable to computer science in part. Now, if you're able to solve this problem, you wouldn't just get a Turing Award, which is kind of the highest award possible in computer science, kind of like the Nobel Prize for computer science. You wouldn't get a Turing Award. The Turing Award would be renamed after you. Like, this is the problem that no one has been able to solve. It is kind of the crux of what we've been trying to think about computation. Now, what I want us to do is I want us to explore some realities here, where let's suppose that P is equal to NP, that solving a problem and verifying a problem are just the same difficulty. What would the world look like if this were the case? So we'll talk in the next video about these things called NP-complete problems. So don't worry, we haven't talked about that term yet. But one of the kind of spoilers, what we're going to introduce is if you find an efficient algorithm for one of them, you find an efficient algorithm for all of them. So we'll talk about that in the next video. But suppose you came up with one of these efficient algorithms. What would happen? Well, you'd win that $1 million, right? That's pretty great. But what's next? Well, you'd put mathematicians out of work, because a huge part of mathematicians' jobs is the fact that finding answers to hard questions about math is not something that's easily automatable. You can't just derive a proof to a hard math problem by sticking it into an algorithm, always. So if we're able to show that, yeah, being able to verify a proof is just as hard as being able to solve a proof, then you can just basically put all mathematicians out of work. You can go prove all theorems that we might care about. You will also be able to essentially decrypt all internet communication. Internet communication relies on this thing called encryption, and most popular forms of encryption rely on the fact that dividing numbers or finding prime factors of numbers is hard. It's a problem that's an NP. So the idea being that if I gave you a large number, you need to decompose it into its prime factors, like the fact that 15 is 3 times 5. Now, doing this prime decomposition is a problem in NP, because if I gave you prime factors, you could easily check if it matched up. You just multiply them together, that's easy. But if I just gave you a really large number, like 371, I don't know if that's a prime number or not, I just picked a number, telling me what the prime factors from that is hard. It's not necessarily in P. And if you were able to show that P and NP are the same, then this prime factorization is just as easy as multiplying numbers, essentially. And since all internet communication relies on the fact that it's technically hard to do this prime factorization, everything would fall apart. There'd be no secure online shopping, banking, messaging, really online anything. Anyone can decrypt your messages because we would have an efficient algorithm to break apart the encryption on your messages. You might potentially be able to find a cure for cancer. I mentioned that protein folding. We don't have to do this try every possibility. You might be able to just divine what the right protein is to cure cancer. But moreover, a world where P is equal to NP is a very, very weird and different place from the world that we live in now. The world we live in now assumes that solving problems is harder than verifying solutions. And if that assumption is not true, things can fall apart for good and for bad. Now, I did mention that this decrypting stuff would fall apart. That's technically true for a lot of things that are in use right now, but there are other tools that kind of can be safe despite if P is equal to NP. But a lot of the assumptions we make about the world would just be wrong, and there would have to be a lot of change. The fortunate news is that most of us don't think this is the case. We think it's really unlikely for P to be equal to N. Most of us think that P is not equal to NP, but if we already expect this to be the case, why do people care about actually proving it? Why do we care about actually spending a lot of time talking about it, thinking about it, even if we're really, really certain this is going to end up being the final answer? Well, trying to solve this problem does tell us a lot about problems in general. It tells us something fundamental about the universe and computation, that solving problems is harder than validating solutions. Now, and it would tell us that there is this kind of fundamental limit that for some questions, there's not always a clever way to find the right answer, even though you'll know the answer when you see it. So this fundamental difference can help us when thinking about computation more broadly. Now, if we're able to prove that they're different, I mean, we'd make the $1 million, which that's great, but it helps us dive deeper, gives us a chance to learn more about computation. So in order to disprove this, we need to understand problems better. We need to understand why some problems have easy solutions and why others don't. And what is it about these problems that yield these properties? These are things that we currently don't know or don't have strong enough tools to reason about in such a way to prove that these things aren't equal, even though we know or really, really certain that they're not going to be equal. Now, we don't just care about P versus NP because it has a huge effect on what the world will look like, even though that is one reason to care about it. One of the things that we care about from a computer science standpoint is about computing. We care about what are the limits of computing, and this is a really interesting limit because we don't know how to solve it, and we've been trying for a really long time. So that's kind of the broad context. What is this P versus NP? Why do people care about it? In the next video, I'm going to show you kind of a more concrete plan of attack for how we talk about either proving or disproving this P versus NP thing. And this is an important set of problems that I mentioned earlier called these NP-complete problems that show up quite a lot in real-world applications. And it's important to understand kind of what these mean and how we go about it once we know that we have one of these problems. But that is kind of the focus in our